So we start by going to our model wizard. And in this work, we'll be using a 2D space dimension. Which will take us to our physics. So we look for structural mechanics. There we have the solid mechanics, so we add this. And also, after adding this, we'll add electrochemistry, physics. Electrochemistry, then we add the primary and secondary current distribution. And we have the secondary current distribution, which we add. Then we move to the steady. So we'll be using a stationary steady. So just select stationary. And it'll take us to our interface. Okay. So what we'll do is quickly draw geometry. We want to draw the geometry for the pipe with the corrosion defect. We use a rectangle. Locate size and shape. The width will be 2. The height will be 19.1. The geometry. We add an ellipse. Locate the size and shape of the ellipse. Under the A semi-axis, it's going to be 100. And under the B semi-axis is 11.46. And we locate the position. X field will be 1. Y field will be 19.1 millimeters. We look for geometry and search for the booleans and partitions. We select the difference. And object to first we look for the object to add and object to subtract. The E1. That's the object to subtract. And here will be the E1. So object add is R1 and object to subtract E1. Go back to geometry and we have the rectangle. The width of the rectangle will be 2. Let's click build all objects. Okay. So after doing it, the figure should look something like this. As you can see. So I want us to check something quickly. The rectangle. Okay, this part is missing. Should be in the meters. So we change this part to millimeters. I just noticed that there was a mistake at that part. So you go to rectangle 1 and just add millimeters. Just good. So now this is how it should look like. Now we want to load parameters. So we load parameters from file. Let's browse and we search for stress corrosion parameters. Open and reload. So we go to definitions and we select variables. We add our variables. We're going to also load from file. Stress corrosion variables. So now we go to our functions. Let me and under functions, we look for local interpolation. We have to look for the stress strain curve. So depending on if you have an experimental results, stress strain curve, we can load it. Here we're going to use the stress primitive file that we have. We have this stress corrosion, stress primitive interpolation. The load from file. And we locate interpolation from this. We locate the so I want us to add a piecewise cubic. So we change this to piecewise cubic, and also the units to want to ensure that it's in MPa. Sorry, this was type 1 and this is MPa. Okay. Now we want to start working on the physics. Locate the domain selection, go to solid mechanics. We select this tool, and here we have to remove from selection. And this is domain 1 only. And also we go to the linear elastic material. Also, what we're gonna do there is we under the attributes, we're gonna locate the attributes over here, and we'll choose plasticity. And under the plasticity model, we have to find isotropic hardness. And we will make a user-defined. Okay, so depending on the material now, you can choose. Now we've gotten to the material space, so we're going to select the type of material we're going to use. So we click add materials, and another built-in material, we use high strength alloy steel. we add high strength alloy steel, which has been added. So under the high strength alloy steel, we select 2, and we're going to take that from the list. And we have to set the properties. So under the initial yield strength, we want to set it to 806 exponent 6 Pascal. Also, the hardening function in the Young modulus, to 207, Poisson ratio to 0.3. Is hardening, because it's already defined in the variables. Now we go back to solid mechanics, and we want to set initial value for the displacement. Let's go to initial values. Specify U to be 0.0001. Times X, and this is what we have for Y. Now under the physics, we select the boundaries and choose a fixed constraint. And that would be for domain 1 only. shift to boundary 1. And also under the boundaries, let's add a prescribed displacement and select boundary 7 only. And under the prescribed displacement, we check the prescribed in X direction, and value for this would be displacement. We're going to add another prescribed displacement. And that will be for boundary 2. Locate prescribed in Y direction. You have to check it. Okay, so now that we're done with this part, we want to set up the secondary current distribution. Yeah. Now look at the electrolyte conductivity. Initial values. We set up the potential, electrolyte potential, and the electric potential as well. So select domain 1 and remove. Sorry. So now that we selected domain 2 only for the secondary current distribution, if we go to the electrolyte, so from the electrolyte conductivity, we want to use user defined and will be sigma 1. Go to the initial values. And under the electrolyte potential, minus mu A plus O A. So go to the boundaries and look at the electrode surface. So I think this side has to be this electrode surface. Okay, so I noticed that there's a missing boundary that we're supposed to add here, and I would like us to go back to our geometries and recheck if everything is in order. We have our main rectangle, we have our ellipse. Okay, so I've seen where this is from. Okay, this has to be in millimeters. Same here. Same here. Good. So we can have this ellipse over here. So after doing this, we'll be able to add our electrode surface. Okay. The manual. We manually input it. That will be boundary number 9 and 10. So after we corrected that ellipse, I think we didn't add it, forgot to add the units in millimeters. Now that we've done our electrode surface, move to electrode reaction. Locate the equilibrium potential and the value be E equal A. Locate the electrode kinetics. We use the analytic Comsol equation. And paralysis will be I0A and under the analytic Comsol slope being greater than 0, YBA. Locate physics attribute. No, we know attribute. So, okay, I think we add an electrode reaction. Reaction 2. Locate the equilibrium potential. And also, as we did for the first one, the Q, O, C. Okay, the kinetics expression, and that will be the cathodic Doppler equation. Have the IC. Cathodic Doppler slope will be BC. So after this, we can finally measure our